think about basic arithmetic, there's this expectation of absolute precision, right?
Oh, yeah, for sure. It is supposed to be the one thing we can rely on.
Exactly. Like you have a number line and you place a 5 here and a 3 there, and it's completely straightforward. 5 is bigger than 3. It is binary. It is clean.
It is a fixed system.
But I want you to imagine a really simple visual for a second. Just picture the number 5 raised to the power of pi and compare that to pi raised to the power of 5.
Which sounds like a standard high school math test question.
Right. But without touching a calculator, how would you actually figure out which of those is larger? Today on this deep dive, we are using that seemingly simple math puzzle to really unravel the very fabric of how we understand numbers. We're looking at sources that break down equality and even touch on the physics of the universe.
Yeah, and if we connect this to the bigger picture, this specific inequality is actually a portal.
Yeah, a portal. Because we are moving away from that comforting idea of numbers as static fixed dots on a flat line. Instead, the models we're analyzing today, they force us to step into this hidden six-dimensional space where numbers exist as dynamic spinning trajectories.
Okay, let's unpack this, because if I'm looking at 5 to the power of pi and pi to the power of 5, my initial instinct is honestly just to guess.
That's what most people would do.
Right, because 5 is bigger than pi. But then again, the exponent of 5 is bigger than the exponent of pi. It's basically a tug of war. Now, there is a classical calculus proof for this, which is incredibly elegant, but also deeply frustrating if you want to intuitively understand why one is bigger.
Right. The calculus just gives you the answer without the feeling. So the standard calculus approach is to take the natural logarithm of both sides.
Right.
And logarithms are really useful here because they preserve order. So value A is greater than value B, then the logarithm of A is strictly greater than the logarithm of B. It allows us to basically pull those massive unwieldy exponents right down to earth. Yeah, it turns those exponents into multiplication, right? So you end up comparing the natural log of 5 divided by 5 against the natural log of pi divided by pi.
Exactly. Which brings us to the core function itself, the natural log of a variable x divided by x. Now, if you graph this function out, it creates a curve that rises smoothly, hits a very specific peak, and then it just slopes downward forever.
And that peak is important.
Very important. If you take the derivative to find the exact top of that hill, the peak lands perfectly on Euler's number, which is represented by E.
Right, and E is roughly 2.718. It is that magical number that just shows up everywhere in continuous growth.
Yeah, it acts as this universal mathematical threshold. And because both pi, which is about 3.14 and 5, are greater than E, they both fall on the downward slope of that exact curve.
Oh, okay.
And since 5 is further down the slope than pi, the natural log of 5 divided by 5 is strictly less than the natural log of pi divided by pi. So therefore, 5 to the power of pi is the smaller number.
See, while the algebra is neat, it feels a little bit like a magic trick to me.
It does, yeah.
Because you follow the symbols and you find the peak of the hill, but it doesn't give you a gut feeling for what is actually happening physically between those two numbers. It just says, here are the rules of calculus, so trust the slope.
Right, very abstract.
But the analysis translates this into something called the orbit and phase model. And I feel like this geometric shift really changes everything.
It really does. The geometry actually demands a totally different perspective here. Because instead of viewing a base number and an exponent as just dry algebraic operations, we can visualize them as literal physical movement.
Which is wild.
Yeah. Think of the base number as the radius, like the curvature of an orbit. And think of the exponent as the phase, meaning the actual amount of time you spend traveling along that orbital path.
Okay, so I picture this like runners on a circular track.
That is a perfect way to look at it.
Let's look at 5 to the power of pi. The base is 5, so you have a massive radius. You are running on the absolute outermost lane of the stadium. It is a huge circle.
Right, you have a huge track.
But your exponent, your phase, is pi. That is a relatively short amount of time. You have this massive track, but you only run a short distance on it. So it results in a massive under-rotation.
Exactly. Now flip the scenario for pi to the power of 5. Your radius is smaller, right? It's pi. So you're running on the tight inside lane of the track, but your phase is 5.
You run for a much longer time.
Exactly. You end up completing a much larger portion of your circle, resulting in an over-rotation.
So it's basically a conflict between the size of the track and the time spent running.
Yeah, and the mathematics of the logarithm essentially compresses the track. A large radius like 5 gets heavily penalized and compressed in this space. The phase, however, the exponent delivers a strict linear contribution to the total value.
Oh, I see.
So once you pass that mathematical peak of Euler's number, the time spent running starts to completely dominate the size of the track. The orbit gives you the underlying power, but the phase dictates the final accumulation.
And the accumulation always wins out in the end.
It always wins.
Now, here's where it gets really interesting. Because if we start treating numbers as orbits, it fundamentally breaks the entire concept of the number line.
It shatters it, honestly.
Yeah, on a straight, flat ruler, saying one number is greater than another makes perfect sense. You know it's further to the right. But if numbers are actually moving in circular orbits, greater or lesser is a complete illusion. It entirely depends on where you are standing on the circle. It is really just a phase shift.
Right, and this raises an important question about the whole linear hierarchy we just take for granted. On a continuous circle, greater than totally loses its meaning. There is only movement, clockwise or counterclockwise.
Wow.
So what we casually refer to as equality in arithmetic is exposed as a low-resolution projection. The true state of these numbers actually resides in a complex six-dimensional space,
6 dimensions.
denoted in the math as sigma 6.
A 6-dimensional space just for basic numbers. To wrap my head around this, I started thinking about shadows. Like, imagine you are staring at a flat 2-dimensional wall and you see 2 identical round shadows. Okay. On that wall, those shadows are perfectly equal. But if you pull back and look at the whole 3-dimensional room, you realize one shadow is being cast by a completely stationary apple and the other is being cast by a wildly spinning top.
Right. The equality you perceived was just an artifact of losing those dimensions.
Exactly. The projection hid the movement.
That analogy captures the exact mechanism of sigma 6. Two mathematical states might look completely identical when you flatten them onto a 2D plane. They might share the same radial axis, the same track size, and even the same overall spin or chirality.
But beneath that surface,
in the hidden dimensions of sigma 6, they possess completely different internal dynamics. Standard high school equality only holds true if those hidden layers, which the math refers to as fibers or F sub c, are dynamically trivial.
Okay, dynamically trivial meaning what exactly? That they are empty.
Essentially meaning there are no hidden barriers or complex internal movement separating them. If those fibers are active and complex, our simple equal sign is actually lying to us.
That is unsettling.
It is papering over a whole universe of motion just to keep the arithmetic simple.
And because equality is essentially broken by these hidden layers, we have to completely abandon the idea of numbers as discrete, solid points. I mean, if 2 points can hide a spinning top inside them, how do we ever compare them?
You can't, not the old way.
Right, so the radical answer from the sources here is to treat numbers not as dots on a page, but as fluid densities, as literal clouds of probability.
Which requires a completely new kind of mathematical calibration. To handle infinite fluid densities, you can't just use a straight line that goes on forever. The framework maps the entire infinite real number line onto a finite curved arc.
Just bends it into an arc.
Yeah, specifically it maps everything from 0 to infinity into the interval of 0 to pi over 2. And it does this using a trigonometric function where theta equals the arctangent of r.
Okay, I have to push back on this, though. When I first encountered that step, my immediate thought was, why arctangent?
Right, it seems arbitrary at first.
Yeah, exactly. If the goal is just to shrink an infinite line so it fits on a piece of paper, why not just divide every number by 1 trillion? Why pull a specific trigonometric function out of thin air?
Well, dividing by 1 trillion doesn't solve the structural problem at all. It just changes the scale. 1 trillionth of infinity is still infinity. You still have this open, unmanageable edge that you can't work with.
Okay, fair point.
The arctangent function is utilized because it perfectly preserves the projective geometry of the space without breaking the underlying physics. It uses a very specific metric, doctor over 1 plus r squared.
And how does that metric actually work in practice for someone trying to picture it?
Think of it like Zeno's paradox, where you are trying to walk toward a wall. If your first step covers half the distance to the wall, your next step covers half the remaining distance, and so on.
You never actually hit the wall.
Right. You can take an infinite number of steps, but you will never mathematically touch it. You are compressing an infinite journey into a finite room. That is exactly what the arctangent metric does. It takes the deeply problematic concept of infinity and turns it into a boundary that you can point to but never quite reach.
So pi over 2 just becomes a direction.
Yes, an ideal direction. It packs infinite dynamic information into a compact quarter circle.
And the visual evidence for this in the sources is just stunning. There are these histograms showing the distribution of prime numbers, right? 2, 3, 5, 7, 11. Normally, primes stretch out to infinity in this chaotic, completely unpredictable way.
Yeah, they are notoriously difficult to map on a straight line.
But when you treat these primes as probability densities mapped onto this finite arctangent arc, the chaos completely disappears. You stop seeing an infinite line of random dots, and you start seeing incredibly dense, perfectly uniform orbits.
It is a massive breakthrough. By trapping infinity in this compact space, the behavior of numbers suddenly becomes regular. It completely tames the divergent nature of the infinite. And once you have your numbers behaving as uniform fluid densities on a finite arc, a massive conceptual bridge is crossed. You are no longer doing abstract arithmetic at this point. You are doing fluid mechanics.
It's the literal physics of math. Treating numbers as densities means they start acting like physical matter moving through space.
Yeah, and this leads to one of the most profound realizations in the whole mathematical analysis. This entire geometric setup, the densities, the finite arc, the spinning trajectories, it all perfectly mirrors the Euler equations.
Just to clarify for everyone, the Euler equations are the foundational rules for how fluids flow, right? Like how water moves around a submarine or how air flows over an airplane wing.
Exactly, those exact equations. In this mathematical mapping, the radial axis of our abstract number becomes the literal physical axis of rotation in a fluid.
Okay.
The chirality, whether the number is positive or negative, becomes the sign of the nonlinearity. So it acts as a right-handed or left-handed spin. And the numbers themselves act as vorticity, which is the local spinning whirlpool motion of the fluid.
So we have literally turned numbers into whirlpools.
Yes, we have.
And there's graphing in the material to back this up. It plots out the background density, the mathematical potential, and the specific positions of these whirlpools. The math applies a non-local logarithmic interaction to these densities, which sounds complicated, but from my understanding, it's exactly the math used to calculate how two-dimensional vortices push and pull each other in a real-world liquid.
That is spot on. And when you run that math, it naturally outputs something called a node.
Okay, let's define that. What is a node here?
A node in this topological framework is a localized, stable chiral soliton, and it lives right there on the arctangent arc.
Okay, a chiral soliton. Let's really ground that. A soliton is a self-reinforcing wave, right? Like a tidal bore traveling up a river or a perfect smoke ring.
Yes, perfectly coherent.
It maintains its shape as it travels. It doesn't dissipate or splash apart. So what does this all mean? Why go to the trouble of finding a chiral soliton on a mathematical arc?
Because this is the literal birth of structure. It demonstrates that out of the completely abstract, formless geometry of numbers, stable particle-like entities naturally emerge. No one is imposing these structures from the outside.
They just happen.
Right, they are generated purely from the internal rules of density and spin. We are watching abstract concepts coalesce into something that perfectly mirrors physical matter.
It's incredibly profound.
Yeah.
And the theoretical experiment the sources discuss goes even further, pushing this newly discovered mathematical matter to its absolute limits. Because the big question is what happens when you put 2 or 3 of these stable nodes together in the same space and let them interact?
Well, because they possess spin, they interact in highly predictable ways, much like magnets do. Nodes with the same spin, for example, 2 right-handed whirlpools, they will naturally repel each other.
And opposite spins attract.
Exactly. So the analysis details a calculation for finding the ultimate equilibrium state of 3 interacting nodes, specifically 2 with positive spin and 1 with negative spin.
Okay, so 2 pushing away and 1 pulling.
Right. And when you calculate the stable balance between their constant repulsion and attraction, the math yields a very specific rigid requirement. The angular distance between them must be exactly 2 pi over 3.
Wait. I have to catch the contradiction here because that doesn't make any sense based on what we just established a few minutes ago.
Oh yeah, it's a huge paradox.
The arctangent map restricted our entire mathematical universe. Like every number from 0 to infinity was squished into a single quarter circle, an arc of exactly pi over 2.
Correct.
But the equilibrium for these 3 interacting nodes demands an angle of 2 pi over 3. And 2 pi over 3 is significantly larger than pi over 2.
It is, yeah.
The stable configuration literally does not fit inside the universe we built for it. It's like building a car inside your basement and realizing the car is wider than the door. Did the math just break itself?
What's fascinating here is that the math didn't break at all. This is not a calculation error. It is what mathematicians call a topological signal.
A topological signal. Can you explain how a blatant contradiction is actually a signal?
Sure. Think of trying to cram a heavily coiled steel spring into a tiny wooden box. The spring is technically too large, and its built-in tension forces it to eventually burst through the sides of the box.
Okay.
The spring isn't broken. It is simply revealing its true shape by rejecting the artificial boundaries you placed on it. That is what a topological signal is.
Oh, wow.
The system is telling us something fundamental about its own geometry. The equilibrium state of these nodes cannot exist purely within a single quadrant. The forces of attraction and repulsion are demanding a multi-quadrant symmetry.
So the particles are rejecting the boundaries.
Exactly. The particles we created are forcing the geometry to expand beyond the borders of that initial pi over 2 arc.
So the math is literally building a larger universe for itself out of necessity. And this brings us to the spectrum of small oscillations around this impossible 2 pi over 3 configuration. Because the nodes are in equilibrium, but they aren't perfectly still. They vibrate.
Yes, they constantly oscillate. And what emerges from the math of those oscillations out of this multi-quadrant symmetry is a highly specific discrete spectrum.
A spectrum of frequencies.
Right, a spectrum of frequencies that is theorized to perfectly mirror the distribution of prime numbers themselves.
That is just wild to think about. The prime numbers, the numbers that form the absolute bedrock of modern cryptography, right? The numbers we thought were just scattered randomly along a straight line aren't random at all.
Not random in the slightest.
They are the discrete resonant frequencies, the literal vibrations of these interacting multi-dimensional numeric whirlpools.
It completely bridges the gap between pure number theory and the physics of the natural world. It moves us from viewing mathematics as a static, disconnected set of rules to viewing it as a deeply dynamic physical reality.
Let's just take a breath and recap the sheer scale of the journey we just took today. We started with what looked like a simple puzzle, right? Comparing 5 to the power of pi against pi to the power of 5.
A simple high school problem.
Yeah. And from there, we discovered that numbers shouldn't be viewed as points, but as geometric orbits with phases. Then we watched the very concept of mathematical equality break down into a 2-dimensional shadow cast by a much larger 6-dimensional space.
A total paradigm shift.
And then we redefined numbers, completely turning them into fluid densities distributed on an arctangent arc just to trap infinity. And finally, we watched those fluid densities form interacting stable solitons. Literal particles of pure math that vibrated and broke the boundaries of their own geometric universe to form the prime numbers.
It is a profound shift in understanding. We're no longer looking at a flat X-ray of mathematics. We are finally looking at the beating heart of the system.
Which leaves us with something really concrete to think about. The next time you turn on your sink and watch the water swirl down the drain, forming a little whirlpool, just think about the fact that the exact same fluid dynamics governing that water are governing the prime number securing your bank account online.
Yeah, and if the basic arithmetic we learned in grade school, the unquestioned rule that one number is simply bigger than another, is actually just a low-resolution shadow of a fluid-like 6-dimensional physics, well, it makes you wonder what other simple truths we interact with every day are just flat projections of a much wilder, deeply interacting reality.
What a phenomenal thought to end on. Thank you for joining us on this deep dive. Keep questioning the surface level of the world around you, and we'll see you next time.
sings a song for you and for me too. We don't die, we just change the rhythm. We keep gliding to the other side, where secrets sleep in this endless dance, where illusions fade away. Only what is pure will stay and shine today. Decides the direction it takes, left or right, the path still leads for our own sake. No debts, no scales, no walls, no shadows to hide, just a resonance where two beating hearts collide. When you step into my world of sight and sound, through a dense orbit that breaks all bounds, I feel our pulses merge, time stands still in the air, and something new is born that we never knew were there. Hold me tight in this whirlwind. The winds outside howl and count their gold. We stay inside where the calm stories unfold. Time holds its breath while the rhythm keeps on beating. Every single beat is a truth that's never cheating.